I want to welcome everyone there to our Success Factors webinar. My name is Carlos Perez and today's topic is baseplate and anchoring to concrete design. During this webinar we will have a short introduction to RAM Connection Connect Edition, which is Bentley's solution for structural steel connections design. Then we will review the workflow to design and detail base plates. In that sense, we will be revising the different analysis, design and optimization options for the steel plate and for the anchoring to concrete. And finally, we will go over some considerations of the base plate in bracing frames. RAM Connection has the base plate and anchoring to concrete design for AISC 360 for the plate and ACI 318 for the anchors. Eurocode 3 and Eurocode 1 for the plate and anchors, the Indian standard AS 800, the Australian IS 4100, the New Zealand NZS 3404 and 3101 for the plate and anchors, and very soon we'll be having the Canadian CSI S16 for the plate and 823.3 for the anchors. These standards are all available in RAM Connection standalone mode and also when it's integrated with StatPro, RAM Structural System and RAM Element. The first step will be to define the unit system. In the status bar, at the bottom right, select the desired unit system. In this case, we will be working with the English one. Not only the main system can be defined, but also specific ones for all the values for modeling and for the reports. In order to check the specific units, just press the units configuration button. This will open the units configuration dialog, where it's possible to customize all the required units. This can be changed at any time. Then we need to define the load cases that we will be using to assign loads. Load cases and load combinations are managed using the Load Conditions Manager. This is found in the Home tab in the Load Conditions group. Let's define two load conditions, one for the dead load and other for the live load. As you can see, dead load is always created by default when creating a new model. In this case, we only need to add a new one for the live load. So let's enter the load case ID. In this case will be LL. Live load as description, and we will assign a category as live load. This is used for the automatic generators to assign the correct load combination factor. Combinations can be also entered manually at the bottom of the dialog. There you only need just to add an ID and start setting the load combinations factors. In this case we can set 1.2 for the dead load and 1.6 for the live load. You can see in the text editor how the load combination is formed. Let's delete this one. It is also possible to generate automatically the load combinations. In the Load Conditions group, press the Generate button. This will show the Generate Load Combinations dialog with different options. In this case, we'll be using for the AISC code the ASCE factored load combos. Let's press Generate, and the tool will prompt us that it is possible to generate just two load combinations according to load cases we already defined. So for the first example, we will only consider the second one. Let's press OK, and the load combination has been generated. All the load cases and load combinations added to the model can be reviewed in the load conditions combo that is located in the status bar. For this example, we have added two load cases and one load combination. Now that the conditions and combinations have been defined, we can start modeling the joint. In order to create a joint, we'll go just to the Joint group in the Home tab and press New Joint button. This will open the New Joints dialog. A joint is only the conjunction of structural members where a connection is required. Currently, RAM Connection can create joints for frame type connections and truss type connections. Let's select frame type, and for the joint let's select the column base CV joint, which we will use to assign base plate connections. The dialog will prompt us the data we need to enter for the column base joint. In this case it's only the column info and the brace info if we plan to add a gusset base plate connection. For the first example, we will only work with a single column base joint, so I will select no brace for this column base. Let's define the column as prismatic member. This means that it has a constant depth over its length. It's also possible to define the column as tapered if required. We'll use a W12 by 96 and a material of A992 grade 50. Once the information for the joint has been defined, we can start adding loads. Loads are defined in the Loads tab. You can see that it's possible to add them for the two load cases that we have previously defined. Let's consider an compression axial load of 120 kips for the dead load and 348 kips for the live load. I'm setting both values negative according to the coordinate system. In this case, axial, it's positive for tension and negative for compression. I will press then OK, and we have our joint when we can start assigning the connections that we require. To assign a connection to a joint, we need to define the standard that we'll be using for the design. Standards are defined in the Design tab in the Assignment group. When selecting a design code, the Customize Connection Design dialog is opened. Here are displayed all the available design codes already implemented in RAM connection. In this case, we'll be using the latest AISC 16 LRFD code. There are some other options, like the maximum strength ratio limited, in case we require a more conservative design, or if we want to enable the seismic design for the connections. Finally, at the bottom, we can find all the load conditions that will be considered for the design. In this case, we'll be working only with load combinations, so the load cases need to be unchecked. Let's set. The base plate assignment tools are located in the same group in the Assign button. There it's possible to see all the base plate options in RAM connection, where we have the pin base plate, use it for pin restraints with tension or compression only forces, where the anchors are located close to the center to allow rotation. Then we have the fixed uniaxial major and minor axis, use it for fixed restraints, where the base plate analysis is performed separately for major and minor axis respectively. Then we have the fixed uniaxial both axis base plate in case both designs are required. This is usually for base plate with major and minor axis moments. All the above are the most common approaches and the ones depicted in the AISC Design Guide 1. Fixed biaxial base plate is used for fixed restraints, where the biaxial behavior of the plate is required to be addressed. And finally, the gusset base plate, use it for column bases in bracing frames. As for this joint, we only defined compressive forces. Let's use a pinned base plate. The connection assignment dialog indicates that one connection has been assigned to the model joint. Let's close this one. The base plate dimensions, anchor diameter, and effective depth were optimized according to the base plate demands. The graphical area shows a 3D view of the optimized connection, At the right we have the information about the joint, in this case the column section and material. We have also the information regarding the connection, in this case the template that was used, a pinned base plate, and the design code select. At the bottom we have the list of the different connections that we'll be creating for this model. This list is formed by a thumbnail of the connections together with the strength ratio of the critical load combination. In order to check the connections data, we only need to double click in the graphical area. This will open the connection path. The path has the following areas. At the top we have the main toolbar that contains the general commands for saving, printing reports, together with some options to modify the model view. In this zone we have also the traffic light that shows the strength ratio and the general status of the connection. The color green indicates that the connection is okay, the yellow that there are geometric problems, and the red that there are some limit states that have failed during the design. At the center we have the area that shows the 3D or the DXF. In order to switch views, you only need to click at the tabs at the right. That will be the 3D view, and this one will be the DXF. As you can see, the DXF show different views of the connection. Let's increase the fonts a little bit. Let's go back to the 3D view. Finally, in the left we have the edition area, which is a panel that is used to show and modify connection data. This palette is organized in 3 sections. The first one will be the general information that contains the design parameters for the connection, in this case for the analysis, the design criteria, and the optimization. Second will be the joint section that has all the information related to the members that conform the model joint, in this case the column. And finally we have the connector section, in this case with all the info related to the base plate, the concrete support, and the anchors. Any change in the edition area will impact directly the 3D view, the general status, and the strength ratio. The anchors in this case seems to be smaller, 1/4 of an inch. This is due to the compression forces set. As there are no tension in the anchors, the software only sets 4 default anchors to comply with minimum requirements. Let's check the design report using the results button in the main toolbar. The design report is divided in different parts. First we have the demands, then we have the base plate design report, down we have the anchor design report, and finally we have some additional information. Now let's check the base plate design report. This one is divided in 2 sections, the geometric considerations and the design checks. The base plate design in RAM connection for AISC code is based on the design guide 1 and verifies the bearing stress for the concrete support, the flexural yielding at bearing and tension interfaces, and the weld capacities. In this case, as we are dealing with a pinned base plate with compression forces, we have demands only for the axial bearing and for the flexural yielding at bearing interface. The other limit states need to be checked when there is tension in the anchors, therefore the demand is 0. Let's expand the equations. The bearing strength depends on the A2-A1 area ratio. The A1 area is the loaded area or base plate in our case. The A2 area is the projected bearing area. This ratio depends on the dimensions of the concrete support. The farther is the base plate from the concrete edges, the larger the A2 area will be, and therefore the bearing strength will be higher. RAM connection calculates exactly this ratio based on the concrete support dimensions. For this case, we have a ratio of 36. Let's return to the connection pad and make some changes. I will modify the support dimensions to, for example, 30 inches by 30 inches. This will make the concrete support smaller, very close to the base plate area. And I will check again the results. I will enable the equations, and you can see now that the ratio is 3.52. There might be also the case that the user would like to modify this ratio to be more conservative but without modifying the support dimensions. This can be done checking the option to override the area ratio. and entering the desired value, which usually is 1. If we go back to the design report and we check again the equation, we will see that this value has been considered for the calculation. With this new area ratio, this limit state is now failing. For the flexural yielding at bearing interface, the capacity is just calculated using the equation for flexural yielding of a plate, and the demand is determined using the cantilever method. The cantilever length considered for this equation is the maximum of all the possible cantilever lengths. This figure, which was extracted from the AISC Design Guide 1, shows the different bending lines surrounding the column sections together with the cantilever lengths M, N, and the one between the column flanges. I will close the report and the connection path. Let's create a new joint with moments and shear values to check the other design parameters. Then we will consider the same column-based joint. Let's create a copy and then we will modify its loads. We will consider a dead load and live load equal to 100 kips and 160. For the shear we will have 80 kips in dead load and 10 for live load, and for moment we will have 1000 kips per inch for dead load and 1500 kip per inch for live load. As we have some moment, let's assign a fixed base plate. In the design tab, in the assignment group, in the assignment button, let's choose a smart fixed uniaxial major axis base plate. This will assign a connection with optimized dimensions. Let's check the connection path. When dealing with moments, we need to be aware of the different analysis parameters to be considered when solving the bearing stress and anchor tension system. In the analysis section, we have the analysis axis with the options of major axis, minor axis, both axis, and biaxial. For the major axis option, the design is performed considering the axial forces together with the moments about the major axis tree and the shear in 2. The green zone represents how the bearing area is formed for this option. For the minor axis, the axial forces are considered together with the moment about the minor axis 2 and the shear in 3. The both axis option performs the design for both axes separately. And finally, we have the biaxial analysis, where the axial is considered with both moments together, showing a more realistic plate behavior. The AISC Design Guide 1 provides some equations to determine the bearing length and the tension at the anchors for uniaxial analysis. Then we have the pressure distribution, which could be uniform or triangular. And finally, we have the strain compatibility option. The uniform distribution considers that the maximum bearing stress below the base plate is uniformly distributed, and together with the tension at the anchors, the bearing length is found. The triangular distribution works in the same way, but instead a triangular distribution is considered for the bearing stress, where also with the tension at the anchors the bearing length is found, as the centroid of the bearing stress in this case is located more towards the base plate edge. This increases the eccentricity that could be considered. When the strain compatibility is enabled, an additional constraint is added to the system, where now it's required for the anchor bolt strain to be in agreement with the concrete strain. This helps to find a solution where the regular method could not. Let's change the analysis options to be in agreement with the AISC Design Guide 1. We'll pick a uniform distribution and we will disable the strain compatibility. Consider that we want to try some base plate options by ourselves. In this case, for example, a base plate of 19 by 19 inches with 2.5 inches for thickness. We want to be conservative, so for the area ratio we will consider the value of 1, and for the anchors we'll consider 2.5 inches as distance to the edges. If we go to the report, we'll see that for this configuration, the regular method could not find a solution for the load combination that we are trying. So the report recommends us to change the plate dimensions or enable the strain compatibility option. I will close the report and I will try first enable the consider strain compatibility. As soon as I enable this option, you will see that the base plate has found a solution. If we go for the other option, we'll have to increase the base plate dimensions. Let's try it with 22 by 22, and you will see that for these dimensions again a solution is found. If we check the report in the additional information section, we can see two figures. The one in the left shows the bearing stress and the one in the right shows the tension at the anchors. In this case, we have a constant value of bearing stress as we have chosen the uniform method. But if we change it to, let's say, triangular, we go again to the report, we will see that for this new analysis method we have a new bearing stress distribution. I will leave it as uniform. We are still with a yellow status. This is because the anchors are too close to the base plate edges for the current diameter. Let's reduce them to 1.5 inches. Now the status is green and we are good to go. The design report shows demands for the flexural yielding at tension interface and for the welds. If we expand the equations, we could see how these were calculated. Again, the flexural yielding is just the flexural capacity of the plate, and the demand is the moment caused by tension at the anchors over an effective weight. When we are dealing with large base plates or large tension at the anchors, it's possible to use stiffeners. In the base plate section, we can choose between stiffener plates and stiffener channels. Let's select stiffener plates. Let's check the top view of the base plate. You can see here how the plates are located surrounding the column section. These modify the bending lines and reduce the distance to the anchors, and as a result we have a smaller moment. Let's check the report. Let's leave it as unstiffened. There are three ways of transferring shear from the column base plate into concrete. First will be by the shear in the anchor rods, which is the option by default. Second, by the friction between the base plate and the grout or concrete surface. And third, by the use of a shear lag. We'll discuss shear at anchors when we'll be dealing with the anchor design. Then we have the friction between the base plate and the concrete surface or grout. To enable this option, we go to the design criteria section and check the option to include friction between base plate and support. If we want to use a shear lag, we go to the base plate section and we enable the include shear lag option. This will display a new section for the shear lag where all its data needs to be entered. First we have its orientation, where you can choose between longitudinal or transversal direction. If we choose longitudinal, you can see how the shear lag is going to be located. So in this case, the lag will act against the B3 shear, and if we choose the transversal direction, that is the one that comes by default, the shear lag will act against the B2 shear. We have the option to consider the width of the shear lag the same as the base plate, or entering some dimensions if this is required. We need to set its thickness, the weld type, that can be fillet or full penetration, and if we choose fillet, we need to set the weld and the weld size. Let's see the report. As you can see in the base plate design, a new section has appeared. This new section is just for the shear lag capacities. In this case, we are based the shear lag design in the AISC Design Guide 1, and we are checking the bearing against the concrete, the shear of the concrete, and for the shear lag plate we are checking the flexural yielding and the weld capacity. Let's turn off the shear lag. Let's check the report again. The anchors are designed using ACI Code Appendix D, which lately was moved to chapter 17. For tension, RAM connection checks the anchor steel capacity, the breakout of a single anchor, breakout of a group of anchors, and the pull-out capacity. For shear, the software checks the anchor shear capacity, the breakout of a single anchor, breakout of a group of anchors, pry out of a single anchor, pry out of a group of anchors, and finally the tensile and shear interaction. Let's expand the equations. For the anchor steel capacity in tension, the capacity depends on the anchor effective area and the material. The check is reported for the most demanded anchor. Tension forces at the anchors are reported in the additional information section. There you can see a table. The anchors are reported with its coordinates related to the center of the base plate and the shear and tension demands for each of them. In this case, as you can see, only 2 anchors have tension, as the other 2 are still in the bearing zone. Let's check now the breakout capacity of a single anchor. In this case, the capacity of each anchor in tension is determined and compared with its demand, and the critical one is reported. To determine this capacity, we need first to calculate the failure areas. The failure breakout areas, as it is shown in this figure, depend on the effective depth, as it is conformed by a square of 3 times this dimension. When anchors are too close, these areas intercept and form what is called an anchor group, having as a group the failure area that is the union of the overlapped areas. Therefore, when we are calculating this capacity, first we determine the edge distances. Here you can see the 4 edge distances: left, right, top, and bottom. In this case, none of these distances intercept an edge, so when we need to check if the anchor is close to 3 edges, the result is false. If this is true, then we need to perform what is called modification of the effective depth. Then the current failure area is determined, the theoretical failure area is also calculated, and the different modification factors. We have the modification factor for the edges, the modification factor for the cracked concrete, and the modification factors for the anchors that are post installed. Currently in RAM connection we only allow cast in place anchors, but in the future we will have these ones also. The cracked concrete condition can be changed. If we decide that at service level we will have cracks, we need just to go to the anchor section in the connection pad and check the option of cracked concrete. I will return to the report, expand the equations. Now you can see that the cracked concrete at service level is true, and the modification factor in this case is just 1. Then the basic capacity is calculated and the factored capacity is determined. For the breakout of a group of anchors, we need to check the capacity of all anchor groups formed and compare them with their demands to report the critical one. Anchor groups are reported in the additional information section. A representation of the groups formed is displayed together with the table with all the groups information. In this case, we have just one group conformed by anchors 2 and 3, which are the only ones that are in tension, with a failure area of 3056 square inches. Let's try changing the effective depth to a smaller value. In this case we have 15.81 inches. Let's try it, for example, with 5 inches. We can see that as the effective depth is small, the anchor's failure area do not overlap, and we'll have just 2 groups for each anchor. But as soon these areas intercept, a group is conformed. Let's try with another value, something like 10 inches. There we have again only one group. Let's return it to its original value. Let's go back to the report. Let's enable the equations. Then the theoretical breakout area is calculated, followed by the current failure area. We already know that this value comes from the anchor groups table. Then we have the section of the modification factors. First we calculate the eccentricity factor for the major and minor axis, together with the eccentricity factor resultant in case we have both eccentricities. And finally, we have the edges, cracked concrete, at casting placed anchor modification factors. We proceed with the calculation of the basic anchor strength, the nominal value, and the factored capacity. The next limited state is the pull-out of anchor intention. This capacity depends on the net bearing area, which is calculated using the head dimensions. Then, according to the anchor types, we need to calculate the single anchor strength. This equation changes for other anchor types. Then we apply the cracked concrete modification factor to get the nominal capacity, and finally the factored capacity is calculated. In the connection path, it is possible to change first the head type. We have the options to select between square, heavy square, hexagonal, and heavy hexagonal. These options will modify the head dimensions, and the net bearing area will be recalculated, changing the capacity for pull-out. We have also the option to change the anchor type. Ram connection not only deal with headed bolt anchors, but also with L bolts and J bolt anchors. If we try with L bolt anchors, you can see how the graphical area changes to a L bolt type. The same goes for the J bolts. And if we check the design report, we can see that for the pull-out, the single anchor strength now is calculated using the distance from the inner surface of the shaft to the outer tip of the J or L bolt. Let's return it to the headed type. Let's now check the anchor shear capacities. The anchor steel capacity in shear, as for tension, depends on the effective area and the anchor material. When a growth path is included, an additional reduction factor is applied to the factored capacity equation. For our example, there is no growth path, but this can be added in the connection path, checking the option to include growthing. When this is enabled, then we need to enter its thickness. If we go back to the report and enable the equations, we will see that an additional 0.8 factor has been considered for the capacity. The breakout capacity of an anchoring shear depends also on the breakout failure area. This area is calculated as it is shown in the figure from the ACI 31811. They depend on the anchor edge distance and the thickness of the concrete support. As in the case of the groups for tension, when the failure areas overlap, they conform an anchor group. In the case of the breakout of a single anchor, the capacity of each one is calculated, consider they act alone, and the critical is presented. We first calculate the different anchor edge distances, and we determine if these are close to the concrete edges. If at least 3 of these distances are close, as in this case, we need to apply a modification to the edge distance to be considered for the failure area calculation. Once we have the modified edge distance, we proceed to calculate the current shear breakout area and the theoretical shear breakout area. Then we determine the different modification factors for the edges, the cracked concrete, and for the concrete support that has thickness less than 1.5 the edge distance. Then we proceed for the basic anchor breakout strength, and together with all the modification factors we determine the nominal capacity, and finally the factor capacity is obtained. For the breakout of group of anchors, first we need to check the anchor groups formed. These are reported in the additional information section. Here you can see a representation of the groups together with the table with all the info. In this case, we have 2 breakout groups, one conformed by the 4 anchors and the second conformed just for the anchors 2 and 3. For the shear, we consider that all the shear force that is transmitted to the concrete is equally applied to all anchors. You can also see that in this case, the anchor groups are not starting in the anchor point. This is because these anchor groups has been modified and corrected as they are too close to the concrete edges. Let's go back to the anchor groups report. Then we determine the theoretical failure area. We have already the current shear breakout area from the table. Then we proceed to calculate the different modification factors. First, we have the modification factors for the shear eccentricity. We assume that the eccentricity in this case is 0. Then we have the edges modification factors, the cracked concrete one, and finally we have the factor for the concrete support thickness when it's less than 1.5 the edge distance. Then we calculate the basic anchor strength for concrete breakout in shear. Then we proceed with all the modification factors and the areas ratio to calculate the nominal capacity, and finally we have the factored one. Let's see the connection path. In the anchor section, we have the option to enable the anchors welded to base plate. If we check this option, we'll consider that the total shear will be critical on the rear anchor or group of anchors and its projected area. This means that the anchor or group of anchors that are farthest from the concrete edge will be considered as critical during the design. Let's go back to the report. The next limit states that we need to check are the pry out of anchor and group of anchors in shear. Let's see the equations. As it is possible to see from the nominal capacity, it's just a factor multiplied by the nominal breakout strength we already calculated. The factor only depends on the effective depth, and it's 1 when this value is less than 1.5 inches and 2 when the effective depth is larger. Finally, we have the shear and tension interaction. This check is determined using the critical capacity for tension and for shear. To find the tension shear interaction, we need to sum the strength ratios of these both capacities, and the result should be less than 1.2, which is the limit established by the ACI code. For current connection, we have a value of 1.23, which is higher than the limit, so this connection is failing. It is also possible to define anchor reinforcement. At the end of the anchor section in the connection path, you can choose between primary or supplementary reinforcement, and if this will be effective for tension and shear. When supplementary reinforcement is selected, then the strength reduction factors will be modified to be considered as condition A according to the ACI code. Let's try, for example, for tension. If we check the concrete breakout capacity, we will see that a 0.75 reduction factor is now used instead of the 0.7 factor that was before. If we choose primary reinforcement, let's say for both tension and shear, we need to enter the reinforcement information, which is the bar size, its grade, and the number of bars. Like, check the report. The breakout capacities for tension and shear are no longer reported, as this limit states will not be critical due to the reinforcement action. Instead, the capacity for the reinforcement in tension and shear is presented. In this case, both capacities are failing, which means that we need to increase the bar size or consider more bars. Let's return to the connection path. I will turn off the reinforcement. The connection can be optimized at any moment. This can be done just by pressing the optimization button in the main toolbar. However, there are some options that might be useful. You can see all the optimization parameters in the optimization criteria section, where it is possible to enable or disable several parts of the connection during the optimization process. Let's say that we already decided the plate dimensions, as in this case, and we only need to optimize the anchors. So then we just need to disable the base plate dimensions, and having the anchor parameters checked, I will press the optimization button. Then you will see that the anchors have been optimized and I have a better ratio. Or we have already decided what anchors we will use, but we need to optimize the base plate dimensions. We will leave the parameters by default. So let me just change the base plate to something larger. I will press now the optimization button. you will see that ramp connection will look for all the options and will present the dimensions that gives a strength ratio closer to 1. Let's save the connection and close the connection path. Now let's create a column base joint for a bracing frame. I will copy again to the joint and edit it. Ramp connection currently is able to define two braces located in opposite sides of the column. Let's consider just the right one. So we need to enter the brace info. As you can see, it is possible to set I sections, hollow sections, rectangular and round, channels, single angles, and T's. For this case, let's select a W section 12 by 22. For the material, A1992 grade 50. And let's say we have 45 degrees of slope angle. Then we go to the loads and assign the brace loads. Let's presume that the brace will be in tension, so 40 kips for the dead load and 60 for the live load. We'll press OK, and then I will go to the design tab, to the assign tool, to the base plate connections, and I will choose a smart gusset base plate. Press close. There you can see the gusset base plate that has been assigned. Let's edit the connection. As you can see, the addition area in the connection path is larger, as it contains the information of the gusset and the information of the base plate. For this example, we'll just focus in the base plate parameters. First, we need to discuss the loads. The figure shows the loads for a column base with one brace. There you can see the column loads and the interface loads from the gusset to the column and gusset to the base plate connections. Ramp connection considers rigid plate behavior for the base plate. Then the loads considered for the analysis are just the resultant. In this case, the moment will be just the column moment plus the interface moments, which most of the cases are 0, plus the moment caused by the vertical force in the gusset base plate interface, plus the moment caused by the horizontal force in the gusset to column interface. The axial and the shear loads are just the sum of all vertical and horizontal forces of the system. Besides all the design parameters discussed for pinned and fixed base plate, the gusset base plate has a pair that are exclusive. The first one is to include the contribution of the gusset and stiffeners in the base plate design. This option is used to determine if the gusset plate will act as a stiffener. Due to the base plate dimensions and the gusset plate thickness, there has been a lot of discussion if this really acts as a stiffener. As a result, we have decided to leave that decision to the user. The way that this parameter works is as follows. Let's open the connection path help. When the parameter is checked, the gusset acts as a stiffener. Therefore, the bending lines considered for flexural yielding are the ones shown in the figure. So the bending lines will surround the gusset and the I section. If the parameter is not checked, then the bending lines are just as in the design guide 1. In this case, we will have a cantilever length larger and we'll expect a larger moment. Let's see. In this case, we have a moment for the flexural yielding that is 3.43, and if we include the contribution of the gusset, we'll have a moment that is 2.93 as the cantilever length has been reduced. Another option that we have in the same sense is to include the gusset well in the tensile force check. In this case, if we check this option, the weld that surrounds the gusset will be considered effective against the tension of the anchors, and if this option is not checked, then just the welds surrounding the column section will be the ones that will act against the tension in the anchors. those will be the parameters we need to check when dealing with gusset baseplate. Other parameters are exactly the same as in the fixed or pinned configurations. Let me close the help. Let's check the detailing for this connection. You will see that as this contains several parts, the detailing is divided several DXFs. In the case for the base plate, as it was shown before, let me increase the font. I have the top view with the base plate and all its dimensions, the lateral view, the front view, and the anchor detailing. Let me save this connection and close the connection path. Let me open a model. Here you can see a few more examples of pinned base plates. Not only eye sections but also round and rectangular hollow sections are permitted. A few examples with stiffeners for eye sections, and finally some other bracing connections. Once that we have reviewed the base plate and the anchoring to concrete design and optimization workflow, we are finished with the webinar. Thank you all for your attendance. If you have any questions regarding this webinar, please reach out to myself and our team of Bentley experts on the Bentley Communities Forum listed on the web page for this webinar, or visit our forum on communities.bentley.com.